I'm doing this video about different ways of drawing organic molecules. So even before I start drawing organic molecules, let me remind you that organic chemistry is all about carbon-based molecules. So I will take a few steps back and go back to Lewis dot structures and start from there. So the electronic configuration of carbon is 1s2, 2s2, and 2p2. So 1s has 2 electrons, 2s has 2 more electrons, and then 2p has 2 more electrons. And this is the ground state configuration of carbon. This is how carbon looks in the ground state. However, in the excited state, so when you give your carbon atom some excitation energy or activation energy, nothing happens here. So your core electrons stay the same. However, there is a little change that happens in these valence shell electrons. Valence shell electrons. So there is one space available right here. One of these electrons jump from here to here so that all of these electrons can sit unpaired. So electrons are like charges. They don't want to be paired in the first case. However, the 2s was lower in energy than the 2p. So these 2 electrons had to occupy this subshell before you could fill up these positions. So now, when you can provide some excitation energy, which is the activation energy, one of these electrons can jump from the 2s level to the 2p level. So now you can see that carbon has space for 4 things to come in and bond with it. So carbon, the Lewis dot structure is 1 electron, 2nd electron, 3rd electron, and the 4th electron. 1, 2, 3, 4. And something else can bond here, 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 and here. And that is how you would make 4 bonds. So carbon in its neutral state likes to make 4 bonds. 1, 2, 3, and 4. And each of these bonds is made up of 2 electrons. Now, the simplest organic molecule that we can think of would be carbon with 4 hydrogens. Hydrogen was 1s1. Your s orbital just has space for 2 electrons to come in. So hydrogens here are actually sharing their electrons with the carbon. So 2 electrons belong to carbon as well as to the hydrogen. So this hydrogen has 2 electrons. That hydrogen has 2 electrons. This hydrogen has 2 electrons. That hydrogen also has 2 electrons. However, the carbon has 1, 2, 3, 4, 5, 6, 7, and 8 electrons because this is covalent bonding. So all those electrons are shared. So my hydrogen is happy with 2, each of those. And then carbon is happy with 8 electrons in its valence shell. Now, we also learned from VSEPR theory, which was valence shell electron pair repulsion theory, that this is not the actual structure of CH4, which is carbon attached to 4 hydrogens. The actual structure of this molecule is a tetrahedral, which is 1 bond right there on the plane of the paper, another bond right here on the plane of the paper, one of these bonds coming towards you, which is said to be on the wedge, and then another bond on the dash. So this is bond on the plane of the paper, both of these. This bond is said to be on the wedge, which is towards you. And then this bond is said to be on the dash, which is away from you. So what does that even mean? So if you look at this molecule, I made a molecule in its tetrahedral geometry. Let me get my papers out of the way. I made this molecule in tetrahedral geometry. This is carbon. These are the 4 hydrogens. The way I drew it, think of this being the plane of the paper. So 2 of these hydrogens are sitting on the plane of the paper. One is towards you, one is going backwards, like behind the paper. So this is coming towards you, like up from the level of the paper, and this is going behind the level of the paper. So this is a tetrahedral geometry. When I drew my CH4 molecule first as a square, these bond angles should have been 90 degrees, but that would mean these electrons are too close to each other. This is just the representation of your molecule in 2-dimensional space. But honestly, these molecules are in 3-dimensional space, so they don't need to be a square. The farthest apart they can be, which is according to valence shell electron pair repulsion theory, these are all negative charges. They all like to be as far apart from each other as possible. In a 3D space, the farthest they can be is 109 degrees in some minutes. So that bond angle is 109 degrees. This bond angle is 109 degrees. So is this, and so is that one. And that's what tetrahedral geometry of your molecule tells you. So this geometry of the molecule is tetrahedral geometry. Now, one technique that I have found extremely handy in my experience with organic chemistry as a student is writing. I write down almost everything I hear and talk about. And the more I write, the more I have realized the gaps in my learning as a student. So I would highly encourage you to write down everything you read in organic chemistry. I don't want to leave these bonds open, so I'm just going to attach these 2 hydrogens. Now, before I jump on to big molecules, let me tell you that my focus in this little lecture would be about a family of organic compounds known as the alkanes. So organic compounds, the more you learn about them, you will see there is a lot of different types. The simplest ones are the alkanes. The alkanes are saturated hydrocarbons. Hydrocarbons would be carbon-hydrogen molecules, and saturated would mean they are full with hydrogen to the maximum possible capacity. So saturated hydrocarbons would mean maximum possible number of hydrogens attached to the carbon backbone. Now, let me draw. I'll go back and kind of repeat what I did, but in different words this time. So my alkanes would have all carbon-carbon single bonds. Alkanes will have all carbon-carbon single bonds. Now, the simplest possible alkane is just 1 carbon long. It's just 1 carbon long, and it has the name of methane. 1 carbon long, and it has the name of methane. 2 carbon long molecules would be called as ethane. I hope you realize that the end of the name tells you what family your molecule belongs to. So that ane comes from alkanes. Ane right here comes from alkanes. A 3 carbon long molecule goes by the name of propane. You must have heard about this, propane cylinders. A 4 carbon long molecule goes by the name of butane. Again, name ends in ane. And carbons are not the only things. There has to be hydrogens as well. I'm going to draw those structures in a little bit. So 1 carbon long would be methane, 2 carbons long would be ethane, 3 carbons long would be propane, 4 carbons would be butane. 5 carbon onwards, the name kind of becomes a little more self-explanatory with the number of carbons. So 5 carbon long is known as pentane. 6 carbon long would be hexane. 7 carbon long would be heptane. Not septane, it is heptane. 8 carbon long would be octane. 9 carbon long would be nonane. And 10 carbon long would be decane. And that's all we would do. Okay, now let's start with methane. Since that's the simplest organic molecule that we can think of, let's start with methane. Let me get this paper out of the way so that I have a little more space to work on. And here is methane. So we would be drawing methane in different ways. Now, if you want to draw methane using Lewis dot structure, then I should draw a carbon with 4 of these dots. And I know that methane has 4 hydrogens because a carbon in its neutral state can make 4 bonds. So I need to bring in 4 hydrogens so that my carbon can have its octet full. So each hydrogen is coming in with 1 electron of its own. And that is how you have a carbon bonded to 4 hydrogens. So the formula for methane is CH4. Now, another way of drawing the same thing would be known as the complete structure of the molecule. Complete structure of the molecule. How would you draw the complete structure? Well, complete structure is kind of the 2-dimensional structure of the molecule. I would draw the carbon in the middle, and instead of showing those dots, those electrons, I would show 4 bonds with 4 hydrogens. That's the complete structure of your molecule. Another way of representing the same molecule would be using condensed structure. In condensed structure, basically we stop at each carbon and write down the carbon part and the number of hydrogens that go with that carbon. Well, with a molecule this small, like CH4, it's really hard for you to see what the difference is between a condensed structure and the molecular formula because both look the same. But once I start drawing a little bigger molecule, things would start making a little more sense. But before I move on to that, I would draw the 3-dimensional form of your molecule, which is the carbon with the tetrahedral geometry and 4 hydrogens attached. Let's look at ethane. Probably we would do ethane and propane, and I think drawing molecules will start making sense to you. So the next one in line is ethane. We know ethane molecule is 2 carbons long. So for ethane, I would draw a carbon-carbon bond. I would draw a carbon-carbon bond. Now my carbons, each of them still need 3 more bonds because we learned previously that each carbon needs a total of 4 bonds around it to have its octet full. Right now, I just have 1 bond. The second one could go here, third here, and fourth here. Same with that carbon, it needs 3 more bonds. And since we are talking about alkanes, which have the maximum possible number of hydrogens, we would fill in all of these spots with hydrogens. This is the complete structure of your molecule, ethane. Now, if I were to do the condensed structure, and this is where you would realize that the condensed structure is not necessarily the molecular formula. That was the problem we had when we were looking at methane. They both look the same because it's just one carbon. But now that I have two carbons, or now that I would see molecules with more than one carbon, condensed structure should start making more sense. So I would stop at each carbon and tell you what is attached to that carbon specifically, how many hydrogens attached to that carbon in this case. So this carbon has 3 hydrogens attached. The other carbon also has 3 hydrogens attached to it. Now, some people draw this bond between the 2 carbons. It's not a hydrogen-carbon bond. It's 2 carbons bonded. The hydrogens are still attached to the carbons. Some people also don't draw the bond and just write them side by side. Both are correct and both are the condensed structure of your molecule. However, don't join everything up together and do not put it as overall number of carbons and hydrogens, because that would make it the molecular formula. So now if I were to do the molecular formula for this molecule, then I would have to add the 2 carbons together. So I have a total of 2 carbons and a total of 6 hydrogens. But it doesn't really tell me how they are attached. Condensed structure gives me a better representation of how they are attached. Let's look at propane. And again, every time you see one step ahead, the previous step makes more sense. So I'm going to draw propane. Now we know propane would be 3 carbons long. So 1 carbon, a second carbon, all carbons are single bonds because this is the family of alkanes. Alkanes have all CC single bonds. So 3 carbons all joined by single bonds. And then we are just going to fill up the octet for each one of those carbons. If this carbon already has 1 bond, it just needs 3 more to have its octet full. This carbon already has 2 bonds. It needs 2 more to have its octet full. This carbon has 1 bond, so it just needs 3 more to have its octet full. And again, since we are talking about the family of alkanes, see the name ends in ane, all of these positions are just hydrogens. So this molecule will fill it up to the maximum capacity with hydrogens. This again is the complete structure of your molecule. So I kind of show all the bonds and everything attached to those carbons. If I were to draw a condensed structure of this molecule, I would stop at each carbon and say what is attached to that carbon. So this carbon has 3 hydrogens, CH3. You can choose to show the bond. The next one has CH2, 2 hydrogens with that carbon. And then the third one again is CH3. Again, like I said, sometimes people draw the bonds, sometimes people do not draw the bonds. But then again, please do not add up all the carbons and all the hydrogens and group them together, because that would be the molecular formula and not the condensed structure. The molecular formula does not tell me how things are attached. Condensed structure does tell me how things are attached. I know there are 3 carbons in a line, and then for the first carbon, I have 3 hydrogens. For the second one, I have 2 hydrogens. And for the third one, I have 3 more hydrogens. So that's complete structure. That's condensed structure. You have seen both of these for the other examples as well. There is a new one that I would show you for this one, which is known as line angle formula or skeletal structure. Line angle formula or skeletal structure. So line angle formula basically is, I'm going to actually make this molecule and show you. So I have 3 separate kind of methanes made. I'm going to, instead of keeping them separate, I'll just join them up. So here is my ethane molecule. I have 2 of them attached. And then for the third one, again, I would take a bond off and attach a third carbon, attach a third carbon. Now, I want you to just look at the carbon skeleton of the molecule. So it's a line angle formula. I would draw the lines between the carbons and at the correct angle. So I would draw a carbon, and then I would draw a carbon that's lower to that, and another carbon going up. So it's the zigzag form of your molecule. Remember, we were drawing these in two-dimensional space, but these molecules are actually in 3D space. So since each of these carbons are tetrahedral, once you actually join them up, they have this zigzag pattern. You can either draw it this way, exactly how I have it lined. So I could draw the first carbon, the second carbon, and the third carbon. Or I could have drawn it this way, which is I could have started here, gone up, and then gone down. It's the same thing. You're just rotating the same molecule and looking at it. So either one of those is fine. Now, the main thing to remember for the line angle or the skeletal formula is that we don't mark the hydrogens. So the rule says that you just draw these lines between the carbons. So the end of each line is a carbon. So there's a carbon here, there's a carbon here, there is a carbon here. So there are 3 carbons. Or if you chose to draw it this way, end of each line is a carbon. So there's a carbon here, there's a carbon here, there is a carbon here. So it's a good idea to have that on your notes. End of each line is a carbon. So the carbon-carbon bonds have to be shown. Carbon-hydrogen bonds do not have to be shown. That does not mean that they don't exist. They still exist. Like if I were to just draw this molecule for you and ask you, what is the condensed structure of this molecule? You, right now, as a student learning this for the first time, best idea would be draw out all the hydrogens and then count and see. We can do one for practice together. So there should be 3 other bonds here, 2 other bonds here, 3 other bonds here, and then you stop at each of those carbon centers and then give me the answer. So carbon-hydrogen bonds do not have to be shown. Nonetheless, they exist. Nonetheless, they exist. That's an important something to remember. You should also know that a carbon attached to a heteroatom, which is an atom that is not hydrogen, like if there was an oxygen or there was a nitrogen or there was a sulfur, you do need to show those. So carbon attached to a heteroatom, so something non-hydrogen, has to be shown. So I want you to remember this. Let's do one for practice. Let me draw out. Let me draw out a bigger molecule, maybe a hexane. You can do butane and pentane for practice yourself. I can do a little bigger molecule with you, maybe a hexane or a heptane. We can do a hexane. All right. That name kind of gives away how many carbons. Hexa is 6. So I should start by drawing 6 carbons. 1, 2, 3, 4, 5, and 6. And then fill out all of these positions, the rest of those, with hydrogens. Again, since these are alkanes, which would be maximum possible hydrogens, this is a hydrogen, hydrogen, hydrogen. Another 2 right here, another 2 right here, 2 more here, 2 more here, and 3 more right there. So this would be the complete structure of the molecule. Now from here, tell me how you would draw the condensed structure. For the condensed structure, again, stop at each of those carbon centers and group the hydrogens around those specific carbon centers together. So if we want to start here, it would be a CH3 attached to a CH2, attached to another CH2, I'm right here. Then this is a CH2, another CH2, and the last one is a CH3. And quickly count the carbons just to make sense, just to make sure that you did not miss something. I have 1, 2, 3, 4, 5, 6, so that should be a hexane. Now the line angle or the skeletal formula, for those, I just need to show the carbon-carbon bonds as lines. I do not need to show a carbon-hydrogen bond. So here is a carbon-carbon bond. I want to start here and go up first. I could have gone down as well. We can do both. So I want to start here. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. All these are tetrahedral, so these would be in that zigzag pattern. If you had 3 more here, so 1, 2, 3, fourth one would be here, fifth would be here, sixth would be here. Or you could have done the opposite way. So I could have started here, gone down, then gone up. Both are correct. So this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. The most common mistakes that I have seen in students would be when they are given a line angle formula and they are asked questions about it, like how many carbons, how many hydrogens, they tend to forget about counting the first and the last carbon. They do remember that these points are carbons, but like the intersection of the two lines are carbons, but the start and the end are also carbons. So please remember that. So that would be hexane. Just to do a little practice problem with you, I do it with my class all the time. I'm just going to give you another structure and see if we can find out how many carbons, hydrogens, and anything else that is present in that structure. So let's look at maybe something a little more than what I see here. So we would do this for practice. So let me do, let's do that. And in one of these, I want to add a heteroatom. A heteroatom is something that is not a hydrogen. So I would put in oxygen. And in the Lewis dot structures, when we did that part, we learned that an oxygen is neutral if it is attached to, if it has 2 bond pairs. So I have to attach it to something else. Let's put a hydrogen. And then it also should have 2 lone pairs. The lone pairs are sometimes marked, sometimes not marked. But that is the other part of the molecule. I want you to tell me how many total hydrogens are present in this molecule. Maybe we should start with how many total carbons are present in this molecule. So number of carbons. So remember, beginning and end of each of these lines, exact lines, would be a carbon, and then each of those intersection points are carbons as well. Unless a point specifically says a heteroatom, it's counted as a carbon. All of these are carbons. And when you show heteroatoms in a line angle formula, a hydrogen that's attached to the heteroatom has to be shown. However, the hydrogens here do not have to be shown in the drawing, but they exist. So number of carbons would be 1 right here. It's a good idea to put these dots when you do it for the first few times, and then you would get used to this with practice. That would be carbon. That's a second carbon, a third carbon, a fourth carbon, fifth carbon, sixth carbon, seventh carbon, eighth carbon, and ninth carbon. So there are 9 carbons in this molecule. Now, how many oxygens are present? I can see just 1 oxygen. A heteroatom has to be marked. So I can see only 1 oxygen. That's not a 10. I'll just write out oxygen so that you don't confuse yourself. Now, last but not the least, let's calculate the number of hydrogens present. Again, like I said, best idea would be to draw out the hydrogens. The first few times until you find your footing in this, draw out the bonds with the hydrogens. This carbon has one bond that is shown, so the other three must be with the hydrogens. So those are the hydrogens. Now this carbon has two bonds, so the other two must be with the hydrogens. This carbon also has two bonds, needs a total of 4. The other two must be hydrogens. That carbon has two bonds, so the other two must be hydrogens. Same here, and here, and here. This carbon has 1, 2, 3 bonds. So the fourth one that's not shown must be a hydrogen. And then on my last carbon, I just see one bond. So the other 3 must be hydrogens. And now you have to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So that is a total of 20 hydrogens. I just wanted to quickly count one more time and make sure that it is 20. Okay, so that was a problem that you can do for practice. So those are some of the examples that I did with you. I would highly encourage to find problems like these ones and try to solve it yourself. Try to go from a drawing like this to a drawing that is a condensed structure. So this would be CH3, CH2, 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 another 3 CH2s, CHOH, and then CH3. So find molecules and then draw those out. If you can leave a comment letting me know what specific molecules you would like me to post, or if you want me to do like a few problems and solve them with you so that you can get a better hang of other type of problems that show up with heteroatoms, I would be happy to do that. I think I will stop this recording right here, and do let me know what kind of other topics you would want me to cover.